Hello, everyone. Good afternoon. My name is Desh. I'm a fifth-year PhD student in the Department of Computer Science. I'm advised by Sanjeev Kudanpur. And in today's talk, I'll be telling you about target speaker methods for speech recognition. Speech recognition is a very old subject. It's been around for decades, for about 50 years or so. At this point, we are so used to the idea of speech recognition that we use it every day in applications that we use on our phones, for example. So we have things like smart assistants like Siri, Alexa, and so on. We use it on Duolingo, for example. We use it when we are talking to customer service bots for voice-based search and so on. If you think about it, all of these are applications that involve a single user talking to their device. What we usually see less often are some multi-user applications. So if you can imagine things like summarizing meetings by first transcribing them and running it through a summarizer, or things like collaborative learning where a device is assisting a peer group in performing some kind of learning direction. These are examples of what is commonly referred to as the cocktail party problem. And I'm not saying that these are not available at all, but it's just that these are less commonly used at this point. And one of the main reasons why that is the case is exemplified by this graph that we can see here. If you can see from left to right, we see that we have benchmarks of common speech recognition data sets. And on the y-axis, we show the word rates. We have things like LibriSpeech, which is clean single speaker audiobooks, which gets very low word rates, even about 2% or 3%. Then we have Switchboard, which is telephone conversations. We have AMI, which is multi-speaker meetings, and all the way to Chime 6, which is dinner party conversations between groups of speakers. As we go from the left to right, the scenario becomes increasingly more challenging, and so does the word rate. And there are several factors which play a role here. There are things like conversational versus read speech. So LibriSpeech is audiobooks, so it's easier to recognize than something like Chime 6, where people are having conversations. It's also the case that AMI and Chime 6 are recorded on these far-field distant microphones. So there's factors such as noise and reverberation that come into the picture. But most importantly, and what I feel is one of the biggest challenges for multi-speaker ASR is the factor of overlapping speech. So we may not recognize it that much when we are talking among ourselves, but humans tend to interrupt each other quite a bit. The studies have shown that in meetings, overlapping speech can constitute as much as 20% of the speech. And in informal dinner parties, it can be anywhere between 30 and 40%. And if that graph doesn't convince you, I have another example here.
I will bring back jobs.
I think a lot about what worked and how we can make it work again.
Well, he approved
Not in your job, take balance, budget.
The single
and
trade deal never approved it.
Incomes went up.
All right. So that was an example of the parliamentary debate between Donald Trump and Hillary Clinton. And if we just run that through any available speech recognition system, which is out there right now, without a doubt, it would fail completely on recognizing, for example, Hillary Clinton's speech, because it just contains a lot of overlaps. And usually when we train such ASR systems, you're not training them to handle overlaps explicitly. You're usually just training them on single speaker utterances. And so at this point, we'll agree that overlapping speech is indeed a big problem for multi-talker ASR. And there can be various methods to address it. In this talk, I'll present one such approach, which is called target speaker ASR. Here's an overview of what this talk will consist of. I'll first define the task of target speaker ASR, and then I'll talk about its application in two different scenarios. The first is a scenario of meeting transcription, which often provides an offline ASR with multiple channels as inputs. I'll then talk about how to apply it in something like voice-based assistance, which is more commonly seen in everyday devices, for example, when you're talking to your phone. Finally, I'll briefly present how to include self-supervised models in this paradigm and incorporate all the benefits that we can get from them. Let's begin with target speaker extraction first. So if we are given a mixed speech as input, for example, the case of the parliamentary debate, target speaker extraction means to extract the speech of a target speaker. And that target speaker can be given to us in various forms. It's usually provided through the form of an auxiliary information. So this auxiliary information can be, for example, an enrollment audio. So for instance, when you usually set up your iPhone, you're required to say, "Hey Siri," 5 times. And that's an example of an enrollment audio. You're feeding your voice to the system so that it can recognize you better later on. It can also be in the form of a speaker embedding or just an implicit context, for example. And we are required to extract that particular speaker's speech. Target speaker ASR, on the other hand, doesn't require you to extract the speech signal, but just to transcribe. So one way, of course, to do that would be first to extract the signal and then pass it through an ASR system. Or alternatively, we can also imagine doing it through an end-to-end system where we don't explicitly extract the speech, but just recognize it. So we don't have to train 2 independent modules for this task. How we do target speaker ASR depends. Yes, please.
Right, quickly, if you were going to apply this to meeting transcription,
Yeah.
Would you run both a Trump model and a Clinton model simultaneously and then have them negotiate?
Yeah, so there's 2 ways. I'll briefly touch upon this later, but you can do first a Trump model and then a Hillary model, or you can also train something which does this jointly so that they can learn from each other. Because
I guess doing it jointly is useful if parts where they're not talking over each other, both models still claim it or both models still reject it, but they know it's speech.
Yeah, exactly. That's one reason why doing it jointly is usually found to be better than doing it iteratively over all the speakers. Yeah, thanks for the question. How we do target speaker ASR depends a lot about on what kind of scenario we are dealing with. So in this talk, I'll focus on 2 scenarios, as I mentioned before. The first is the example of a meeting transcription. The second is a voice-based assistance. And they differ from each other in several parameters. For example, the recording devices. Meetings are often recorded on multi-channel microphone arrays, whereas voice-based assistants, it might be the case that it's just recorded on a single microphone on a smartphone that's present somewhere. In terms of speakers, meetings contain several primary speakers and they are all required to be transcribed, whereas voice-based assistants usually just contain one primary speaker who's talking directly to the device, but there may be other interfering background speakers who can be ignored. In terms of wake words, voice-based assistants consist of utterances that are all often prefaced with a wake word such as "Hey Siri" or "Alexa." And this is an extra information which we can leverage to recognize the primary speaker. And a big constraint that comes with voice-based assistants is that these systems are often deployed on devices. So there's a lot of constraints that come into how big your model can be and what kind of transcription you're required to do. So in this case, we are required to do real-time streaming transcription. Let's start with the scenario of meeting transcription. The problem looks something like this. We have a mixed speech, which is an unsegmented recording given to us as input. This can be anywhere between half an hour, 1 hour long, and even more. And the problem usually is called as speaker attributed transcription, which means that we are required to transcribe all the speech in the input recording and also attribute it to the respective speakers. So in this case, we would say speaker 1 said hello and how are you doing? And speaker 2 said, hi, good afternoon. Here's one approach that can be used to address the problem of meeting transcription with the use of target speaker extraction. It goes something like this. So we have a mixed speech which is given to us as input. We have some kind of a diarization system. So diarization answers the question, who spoke when? And that would give you speech segments, time boundaries corresponding to each speaker. For example, it would tell you speaker A spoke from 0 to 5 seconds, then again from 8 to 10 seconds, so on. You can also use an oracle sometimes for this purpose. And finally, you use this time segments to extract the speech of those speakers and pass it through an ASR system. to independently transcribe or jointly transcribe, as you may, each of those speakers. So the target speaker extraction module plays an important role here in tying these two diarization and ASR systems, because it's kind of like the component that takes the information from the diarizer, extracts those segments, and passes it on through the ASR. So you can imagine that if we want to use this for a real system and we want to iterate on our diarization, because diarization is indeed the thing that starts and it tells you what the segments are. We want the target speaker extractor to be sufficiently fast so that we don't have to wait too long between getting our diarization outputs and the ASR outputs. This is a very flexible system in the sense that you can use any kind of diarization system you want. There's tons of diarization systems out there, and any kind of ASR system you want. And you just tie it together through this target speaker extraction component. And because of this flexibility, this was the baseline that was used in the Chime 6 challenge back in 2020. And it's again the baseline that's currently being used in the Chime 7 distant ASR challenge that we are organizing along with a few other people. The target speaker extraction component in this pipeline usually uses something called guided source separation. So this is an unsupervised signal processing based technique which uses ideas from blind source separation that I won't go into the details here. But the key idea is this. It uses this three-step process. First, it de-reverberates the input mixture to remove any kind of late reverberations that may be happening. And late reverberations happen because these meetings are usually recorded on these in these large rooms, which have a lot of reverberation. And we may not hear it, but it causes a lot of degradation for ASR systems. So we have an unsupervised method which de-reverberates the signal. We then estimate masks, which are STFT masks for each of the speakers in the mixture. This is done through some kind of an EM algorithm with mixture models. And the estimated TF masks are then used along with the original signal to extract the speech of each speaker. So for example, in this case, we can see that the extracted TF masks for speaker 1 and speaker 2 can then be used to suppress the audio of speaker 2. To show you how well this works, I'll play this recording here and see. So this is the original recording. I would like you to pay attention to the last part where there's the overlapping speaker. So there was one primary speaker that was present throughout the segment, but towards the end, there was also an interfering female speaker who we ideally would like to suppress. And after we have run GSS on this segment, we would like to just retain the primary speaker, and this is how it sounds like.
All declares that the false positive all are sent either by man or by man.
If you had noticed, there was we did suppress the background or the interfering speaker quite a bit, and can imagine that this would help the ASR system a lot, because now you know exactly what the primary speaker is saying. Although there is some there is some residual noise from the other speaker as well, but the SNR is high enough that the ASR system should be able to figure it out. So that's well and good. This is nothing new. This has been around since 2018 when it was first proposed by these folks from Paderborn for the original Chime 5 challenge. And they won that challenge because of this system. It contributed to an absolute word error rate improvement at that point, which was about 10%. It's quite significant. But the problem with this algorithm with GSS overall is that it's extremely slow. In the Chime 6 dev set, for example, which is roughly 5 hours, I think, it takes 20 hours to perform enhancement on the whole Chime 6 dev set with as many as 80 jobs. And the main reason is that it consists of a lot of iterative methods in its pipeline, and all of them are implemented on the CPU with NumPy. So we wanted to get rid of this bottleneck because we wanted to use GSS in the new edition of the Chime challenge, and we didn't want to wait one day before we can find out if our diarization system works well. So we put everything on GPUs because that's what everyone does now. And we got big improvements. And this is a paper which is currently under review at Interspeech 2023. And here's what we did. So it consists basically of putting things on the GPU, but doing that smartly. There's 4 major changes that we made. The first is that the original GSS algorithm, it takes each segment one at a time and passes it through all the different components of the pipeline and generates the enhanced segment. When we want to do it on GPUs, this can be painfully slow because one, each segment can be very small, so you're not utilizing your GPU efficiently. So what is usually done to counter this is to batch things together. You cannot do batching in the naive sense of similar to a deep learning pipeline, because a lot of these components play into downstream, the beam forming, for example, which computes statistics over the whole duration of the batch. So what we do instead is, for each batch, we only use segments from a single speaker, and we batch it along the time axis instead of along a new dimension. This kind of creates super segments of a single speaker instead of using small segments of multiple speakers. And this is all done in background CPU-based workers, so that no GPU time is wasted. As soon as we have these super segments in a batch, we put this onto the GPU, and all the remaining compute-intensive tasks, such as STFT computation, de-reverberation, mask estimation, so on, they're all performed on the GPU. Even within the GPU, we do some modifications, for example, to improve the GPU memory utilization. For example, we just do simple things like batching all the frequency bins since they are independent of each other, or things like iron-sum path caching. So a lot of these components involve iron-sum methods, and they are done iteratively for several iterations, for example, for 10 or 15 iterations. So what we do is we compute the optimal path of the iron-sum in the first iteration, and subsequently we just cache it and reuse that path instead of computing it again and again in each of the iterations. These are just simple engineering tricks that help speed up the GSS quite significantly. And we found that instead of taking 20 hours or 19 and a half hours that it used to take with 80 CPU jobs, we can now enhance the same Chime 6 dev set in just over 1 hour. We use 4 GPUs, and these are not even very good GPUs. This is on the CLSP cluster. So I can imagine that would be even faster if you have GPUs with larger memory and you can batch more segments at once. So this implementation is now part of the baseline for the current edition of the Chime 7 Distant ASR Challenge, which is currently underway. And I expect that it will help teams to just iterate over their pipelines faster and to see how well the diarization performs. So back to how we used it in the meeting transcription task. So I showed you this picture before, and we saw that we can use this as kind of like an intermediate step between diarization and ASR. Just to see how well GSS does, we computed the error rates on the AMI dataset, which is again a meeting task with 4 speakers, using 2 kinds of diarization systems. The first is an oracle diarization, so you know exactly where each of the speakers is speaking. And the second is a clustering-based diarization, which gets a DER of 23.7%. When we don't use any GSS, that means that we just cut the segments that the diarization tells us to and use that directly in the speech recognizer. We get 32% and 39% word error rates. And you can see that there are some residual speeches from the other speaker because this has not been suppressed because we're not using GSS at all. As soon as we use GSS for this extraction purpose, we see huge improvements. For example, for the case of an oracle diarization, the worded rate goes from 32% to about 23%. For a clustering-based diarization, it goes from 39 to 31%, so about 20% relative improvement. But even beyond its application to meeting transcription, just having this fast GSS implementation allows us to play with a number of parameters that the original implementation didn't check or didn't have time to play around with. It has always been known that blind source separation or guided source separation in this case improves as we increase the number of channels. By number of channels, we mean the number of input microphones. But now we can put a number to that idea. And we see that as the number of channels increases, the worded rate indeed goes down, but there is still some kind of diminishing return. So beyond 4 or 5 channels, we only see marginal improvements, especially for something like LibreCSS, for which the worded rate is already quite low. But still, it's always better to have more channels in this case. In terms of number of iterations, so as I mentioned earlier, mask estimation is done through mixture models, and it's kind of like an EM algorithm with, and you iterate until you converge to a local minima. The original authors in the original implementation of GSS, they were using up to 15 or 20 iterations, and that takes long because these are each iteration takes some time. But we found that you can use as little as 5 iterations and still get mostly the same benefits. And this helps because the fewer iterations you have, the faster your processing time is. So all these little parameters, there's a bunch of other things we did, which is in the paper, which I'll skip for now. So that was about using target speaker methods for meeting transcription using this pipeline of diarization, extraction, and ASR. I'll pause for a bit and see if there's any questions. All right. As I mentioned earlier, the way we do target speaker ASR or target speaker extraction depends a lot on what kind of scenario or application it's being used for. It's because each scenario comes with its own constraints in terms of what inputs you have, whether you're required to do it in real time or is it available offline, and so on. So the second scenario we'll talk about is this application in voice-based assistants. And it's very different from that of a meeting transcription because now we are constrained to work with just a single microphone. So GSS is completely out of the picture. It doesn't work when you have a single microphone. In terms of speakers, you usually have one primary speaker with some interfering speakers, and the SNRs may vary. We also have access now to something called a wake word or an anchor segment. These are things like Hey Siri or Alexa that people usually preface their utterance with when they're talking to a device. Also, we are required to do it in real time, so we cannot wait until the end of the utterance to start transcribing. This brings us to something called anchored speech recognition, where anchor refers to a wake word. So the scenario looks something like this. There's a person talking to a device and he says something like, Alexa, play my favorite song. But during that utterance, there's another speaker who is maybe talking in the background, and we don't want to transcribe that other speaker. And this can happen very often in a household which has multiple people, and there's one person who wants to get something across to the device, but there's other people talking, and Alexa just misses that completely. So the idea here is that we want to use that information from the wake word segment because we do know that that wake word is indeed spoken by the primary speaker whose utterance we want to transcribe. And we want to use that information somehow to make the transcription better. This is what is referred to as anchored speech recognition. It was first proposed in this paper from ICASP by folks from Amazon. And we take this paradigm and work it into modern neural transducers because this class of models is what industry uses nowadays. So most of the industrial ASR now is based on neural transducers. And we want to see if we can use anchored speech recognition along with neural transducers, just suppress background speech and improve the recognition capabilities of these models. So before we get on with how we do that, let me give you a quick primer into neural transducers. So neural transducers is a kind of ASR model which takes speech as input and generates conditional probabilities for each output token at each time step, conditioned on the whole input speech and all the tokens that have been generated before it. So this is the likelihood that we want to generate. This is done by factoring into 3 different components. The first is an encoder, which is kind of like an acoustic model. It takes the input speech and generates a high dimensional representation of the input speech. The second is a predictor, which is an autoregressive model. It takes all the tokens that have been seen until now and generates a high dimensional representation at that point, at that time step. It can be thought of as similar to a language model. Finally, we have a joiner, which takes the representations of the encoder and the predictor and combines them in some way to generate logits for the output, generates a probability distribution over the vocabulary for the next time step. Usually the encoder consists of stacks of transformers or its variants. Predictor is often an LSTM, and the joiner is often just a simple feed-forward network. So that's very briefly how a neural transducer works. It's very useful because it's streaming, especially when you're using causal masking in your encoder, and it produces an alignment between the input and output in the sense that you know exactly at which time frame each of the output tokens are generated. So here is what we did to bias the transducer, that is to integrate anchored speech recognition in the neural transducer. So the idea here is that we have the wake word segment, which is also the anchored segment, which is the same as saying, "Hey Siri," and we know that part is the anchor segment. We want to use that information to bias the encoder to only generate the hidden representations for the part of the input speech which is spoken by the target speaker. And we do that by adding a small auxiliary network which generates a context representation. And by small, I mean that it only takes up 1% of the model size. So it's, in practice, it's just 2 feed-forward layers with attentive pooling mechanism. This auxiliary network takes the wake word segment, extracts a context embedding, and feeds that into the encoder along with the input features. And then the encoder is trained to learn to suppress anything which doesn't sound like the speech of the primary speaker. So that's one way we bias it. In practice, we see that in cases where the primary speaker is completely silent and there's only the background speaker speaking, this is not enough because this is too far down in the pipeline, in the whole stack, to be very effective at the top. So we also gate the joiner, the output of the joiner. So how this works is that at each small time step, we compute the context embedding of the small time step and compute a similarity score between that segment versus the segment obtained from the wake word. The idea here is that if that segment was indeed spoken by the primary speaker, the similarity score would be high, otherwise it would be low. And so this score can now be used to gate the output of the joiner to boost the non-silence, non-blank tokens only in the case when the primary speaker is speaking. So when the primary speaker is absent, this would boost the score of the blank token, and that would eventually suppress any outputs that would have been generated for the background speaker. So we use both of these methods, the encoder biasing and the joiner gating. And we apply it and we check the performance on mixtures of, yes, right.
So is the joiner predictor encoder parameters updated when you train the auxiliary network, or are they like totally frozen?
No, everything is trained jointly from scratch.
So that means this auxiliary network cannot be plugged into some other ASR system. They have to
Yeah, they have to be trained together. I can imagine that if you already have like a pre-trained system, you can just do like a bit of fine tuning with this added, similar to how we do with adapters, I guess.
So what happens if in a recording we have multiple speakers, one says the beginning Alex, then the second one says Alexa, what happens in that scenario?
That's an interesting one. So usually you have to specify which person you have to transcribe. So in this case, we do that by saying that the person who said the wake word is the person we want to transcribe. The scenario you're describing is, I would consider that ambiguous from the sense of this task. So we cannot be sure what would happen. I haven't checked, but it might be the case that they're both transcribed, for example.
Be nice to check. You can transcribe.
Yeah. Usually these systems have separate keyword spotting, a wake word detector. So the wake word detector, which is activated just before the ASR system takes over, is the one that's used here. So the person who spoke Alexa latest, in this case, the second speaker, they would be considered the primary speaker.
Then the first one will be removed or what?
Yeah, because the wake word detector was activated latest for the second speaker.
It would be nice to.
So would it really bring the person, for example, I say Alexa and Bobby to say something now?
Yeah, so your device is only required to respond to you, not to Bharti. All right, thanks for those questions. Let's look at how this performs. We created simulated mixers based using library speech utterances. We also did some experiments with. I forgot to mention this earlier, I think. This was work done during an internship at Meta last summer. And we also experimented with some in-house data sets, but we cannot show results here at this point. So these are results using library speech mixtures, and they have an average SNR between 1 and 20 decibels. And there's 3 different scenarios here. So on the red shows the speech of the primary speaker, and blue shows the background speaker. We mix them in 3 different shifts, which we call background shift. 0% shift means that the background speaker is speaking throughout the duration of the primary speech. So in this case, you can imagine that even the wake word part is contaminated. And so we don't really expect to see a lot of improvement because the wake word is not clean enough. The 50% and 100% cases denote cases where the background speech starts after the primary speaker has started speaking. And the wake word segment is cleaner in this case. So we do expect to see some improvements here. These are the results that we have. The blue bar shows the results using a regular transducer, which does not have any auxiliary network and does not have any of these biasing mechanisms. The red and the yellow show results when we add encoder biasing and we further add joiner gating. You see that as expected in the case of 0% shift, there is no improvement. There's also no degradation either. So that's good to have. When your whole recording is contaminated by both people speaking, and there's not much you can do to improve things. But when you at least have some idea of some clean wake word segment, you do get like big improvements. In this case, going from 12.4% to 8.3%, which 50% shift, and 26.7% to 14%, the case of 100% shift. And here's what the improvements look like for a qualitative example from this data. This is what the mixture sounds like.
Then they seem to spring from every part of the country.
Nation may be very much modified through dogmas.
So here we have 2 speakers talking. The first is the primary speaker. Of course, library speech does not have the concept of a wake word, so we just took the first 2 seconds of the utterance and considered that the wake word.
So were you just playing gold or extracted?
This was the original mixture.
That's the original.
Yeah. In this case, we are not extracting anything, we are directly transcribing, so there won't be an extracted. Yeah.
You don't have an audio that plays them superimposed.
I don't, but it would have been similar to the audio that I played earlier. Yeah. So this is the case of this 100% shift example, where the first person starts speaking and then the background speaker starts speaking. And in this case, we only want to transcribe the first speaker, which is the reference. The original transducer, of course, does not do that because it's not biased by the speaker information. But the target speaker ASR here, it does perform well in this case. And it suppresses all the speech of the background speaker or the secondary speaker. We also looked at what the context embedding is actually looks like. So remember that we haven't trained the auxiliary network to do anything special about the speaker. We are training it just jointly to recognize the speech of the primary speaker. There is no speaker labels involved here at all. But it does learn to kind of make the context embeddings look like speaker embeddings, in fact. So in this figure, we show the context embeddings generated for all the utterances in the def set, and the colors denote speaker labels. We see that they do get clustered very nicely into speaker clusters. And so this is a good kind of proof of concept to show that the context embeddings are kind of capturing speaker information and not lexical information. We also did a bunch of other things to make sure that content is disentangled from speaker information in the context embedding. So just simple things like auxiliary objectives in the form of feature reconstruction, VIC regularization, which is a popular self-supervised objective nowadays, and so on. But I won't go into the details here. All right, so that was about the anchored speech recognition for target speaker methods. Finally, very briefly, I'll talk to you about how to bring into the picture self-supervised models. And this is important because a lot of the paradigm these days involves taking a self-supervised pre-trained encoder and fine-tuning it on a target downstream task and then using that. That brings all the advantages of the large-scale unsupervised or self-supervised pre-training, but you're still doing well on the downstream task. This is a paper that's also accepted at ICASP this year, and all the work here was done by my colleague Zilli, and I was just making nice tables. So this is how you would do self-supervised learning plus fine-tuning with target speaker ASR. This is very similar to what Jason was mentioning earlier about doing things iteratively versus doing things jointly. So we looked at both of these approaches. So the figure on the left shows how you would do it iteratively. The gray boxes show components from the self-supervised encoder that are pre-trained. And the blue adaptation layer is what we use to bias the encoder with speaker information. We assume that we have some information about the speaker in the form of speaker embedding. We feed that into the encoder in the speaker adaptation layer and kind of biases or changes the representations of the CNN encoder before feeding it to the transformer. And so even if you have a mixed speech as input, it would output tokens only corresponding to the speaker for which the embeddings have been provided. You can try to do that iteratively. For example, if you have 3 speakers in your input mixed speech, you can do it independently for speaker A, speaker B, and speaker C. But you can, but this is kind of not optimal because here we are making the implicit assumption that the output tokens for speaker A are conditionally independent of those of speaker B and speaker C, given the mixture and speaker A's embedding. You can also try to do it jointly and just model the joint probability. And this can be done by having each of these independent modules, but also taking their output representations and just passing them through a simple combined module with jointly models all the representations. In our case, this is just a simple transformer layer, single layer. Here are some results on the AMI dataset, which is, again, if you remember, it's a meeting transcription task. It shows how much improvement we can get if we perform the target speaker extraction based fine tuning iteratively or jointly. The original Wave LM, it does miserably at this task. It gets 100% word rate. If we fine tune it with the target speaker extraction objective, and we do this iteratively, we get 50% approximately word rate. Finally, but if we model all of this jointly and make sure each of the speakers interacts with each other, we reduce the word rate down to 28%. So in summary, we saw different flavors of target speaker ASR, and these are very different from each other, and it depends a lot on what kind of applications they are being used for. So you can have something like GSS, for example, which is very useful for meeting transcriptions when you have multi-channel inputs and you don't require streaming transcription. But if you do require streaming transcription and you have constraints of on-device voice-based assistance, something which would be useful is something like anchored speech recognition. You can even use all the advances in self-supervised encoders by fine-tuning smartly with target speaker extraction and joint modeling objectives. That's all for today. Thank you. Yes.
For the last example that you showed, when the output module is outputting the text for 3 different speakers, is that text aligned to the audio? So is it basically just outputting like token 0 for each speaker at the same time, even if the speakers aren't speaking simultaneously, or is it outputting like token 0 for speaker 1 and empty tokens for speaker 2 and 3 until those speakers start speaking?
Yeah. So in this case, it is aligned because our training objective was based on CTC, if Zilli, is that right? And so as you mentioned, when only one of the speakers is speaking, the output tokens would only be present for that speaker and the others would be blank tokens.
I have another question.
Yes.
So more broadly about the anchored ASR model. So the model you have there has sort of like late fusion between the text and the speech.
Yeah.
Are there models that do the fusion earlier?
So I imagine that by late fusion, you mean the joiner network, which takes so contrary to what you would expect from a regular encoder-decoder model, it has been found that the prediction network is not very important for transducers, and most of the heavy lifting is done by the encoder. So even the encoder, I called it an acoustic model, but in fact, it contains a lot of properties that even a language model would have. So you can, these days, people like in our implementations, we even just use a simple one layer conv 1D prediction network, whereas the encoder is usually several transformer blocks. So there's not much information that is coming from the prediction network. So perhaps using that to fuse earlier wouldn't be that useful.
Okay.
Yeah.
I was wondering how are the speed methods compared to each other? For example, for the anchored ASR method, maybe you can also run the GSS-based system.
We could, yeah. You would have to have multiple microphones, which we do have on Alexa devices contain multiple channels. It cannot do streaming ASR, so it's not very fair to compare a system that does streaming transcription with something that can leverage the full context. But if you did run it on the same data, the GSS would perform better. Yeah.
The way for it is not accurate, so it's the same.
So in practice, what we did was for example, for the in-house data, not all of them contain wake words. So you just train it on the entire data set with or without wake words regardless. And for the parts which do not contain wake word, you just don't propagate the gradients to the auxiliary network. And that way your system just learns to ignore the part where there's no wake word. Yes.
So in the anchored ASR idea, if I understand right, the reason that you use the wake word is because you want a segment which only has the speaker.
Yes, that's correct.
So I guess one question is whether you're sure that there's nobody else talking when somebody is like, we have a smart speaker in my house.
Yeah.
And I think sometimes if I say, hey, Google,
Mhm.
there's other people talking.
Yeah, so that is a constraint right now. We did see that it also depends on the SNR. So if there are other speakers talking, but the SNR is relatively high, which means that you do have one dominant speaker, the system still learns to do well with just that. But if there are two speakers and they're both the SNR is extremely low, they are both equally dominant, then there's not much this system can do with that.
Is your bet that in that case, the wake word won't even be recognized?
Yeah, often that does happen.
So in the cases where the wake word is recognized, probably.
Yeah, it won't help with the speech recognition.
Probably there is one speaker that's prominent. So this takes me to my follow-up question, which is wake word detection the only way to detect that there's only a single speaker speaking? I feel like if I can detect particular words and they don't have to be Alexa or Hey Google,
Mhm.
then just being able to detect them well, or being able to predict the entire signal or something. So like round trip
Yeah,
from text to speech, from speech to text and back to speech is
yeah,
a pretty good indicator that there's only a single speaker. And then maybe you could use that for anchored ASR without having to use the wake word.
yeah. So one reason why we rely on wake words is very application oriented. It's because wake word models are usually present on device and they're extremely small. They're always on. So that gives a good indication of when the speaker starts speaking. We cannot have an ASR system running all the time because of this reason, because they are usually more power hungry than wake word systems.
But isn't the anchoring idea also useful in always-on systems like meeting transcription?
Yeah, it can also be applied to meeting transcription systems, but just the fact that it constrains the model to just to use some kind of embedding or some context to transcribe. And for meetings, if you're doing it offline, you can leverage the whole meeting as context. So you don't just have to rely on one wake word that was spoken at the beginning.
Sure,
Yeah.
So sorry, maybe if people want to go because it's chapter 1. So I can follow.
I'm good if you. And if people want to leave, they can. You can. It's fine.
So what I won't be. So how hard is the following problem? Segment the meeting into periods where only one speaker is speaking,
Mhm.
and periods where there's multiple speakers.
Overlapping speech detection is a huge problem. It's very hard to do.
That's hard.
It's very
because
hard.
It seems easy for me. Like I could be in
Yeah.
a room, I could be at a cocktail party or something
Yeah.
where I don't even speak the language, and I think I can still tell the difference between one person and two different.
Yeah. So if we try to do overlapping speech recognition on this conversation, it wouldn't recognize any of the parts where I said yeah, and all of those segments would be lost. And so if you're doing it to do a summary, there would be no summary saying that Desh acknowledged everything Jason said. So that's the hard part. All recognizing all these back channels usually. If there's a one speaker speaking continuously for an extended period, that's easy.
So for the purpose of finding and embedding the individual and clustering the individual speakers,
Mhm.
maybe it's okay if you don't cut out the back channels.
Yeah, usually it is. But in general, if you want to detect all the speakers, you miss out on any speaker who was the interfering speaker and was the overlapping. You did recognize the whole primary speaker, but we missed out on all the overlapping speakers. So that contributes to a lot of the overlapping error rate or diarization error rate. So diarization with overlaps is also a big research direction. Paola works a lot on that. Right, thank you. Yes, Martin. Mhm. Yeah. Yeah, that's a good point. I think I did bring it up during the project. We didn't have enough time to do all of this stuff. One argument against that is that these systems, they want to use it for devices where you can customize the wake word. So you cannot really train just assuming that it would always be Alexa or it will always be Siri. Yeah, you would. You can leverage that information certainly. Yeah.
Improvements, because for example, in the beginning you mentioned you would have to
Mhm.
say Google and AC pipeline. And then you leverage with the Android ASR in case of devices.
Yeah, so if you don't have the wake word, you can use the enrollment information as a different auxiliary information. But usually, if, for example, you have guests over and they want to talk to your Alexa, they're not enrolled, so, and you don't want to miss out on them.
Yeah.
So for the Android ASR, you show static data, right?
Yeah,
Do you have a sense how good this can be in big data?
it works.
You cannot say.
It works. I can just say it works. Yeah.